You are listening to The Vocal Technologist. Spoken tech for your ears.
Picture this. You have spent months building an absolute beast of a data pipeline.
Right, the dream setup.
Exactly. It is supposed to be a masterpiece of modern engineering. You look at your monitoring dashboard, and it is glowing, this beautiful, reassuring green.
Always a good feeling.
Oh, the best. You are getting all the automated success alerts right there in your Slack channel. You grab a coffee, feeling like a total champion, and then, you open the database to actually query the information.
And let me guess.
Mate, there is nothing there. Crickets. Absolutely zero data has actually arrived.
Yeah, it is a phenomenal betrayal by your own infrastructure, honestly, because you have this complete illusion of operational perfection on the surface.
Right.
While underneath, you are experiencing total systemic failure. The monitoring tools are essentially just giving you a false sense of security.
And that is exactly the phenomenon I want to unpack here on Vocal Technologist. We are looking at a stack of engineering blogs, benchmark reports from the folks at DuckDB, and architectural white papers from companies like Uber and Pinterest.
It is a fascinating collection of problems.
It really is. The overarching theme we're going to explore is the illusion of scale. We're going to look under the hood of pipelines that straight up lie to your face.
Which happens way more often than people want to admit.
Oh, absolutely. We will also get into the hilarious reality that your shiny new autonomous AI agents cannot actually read your company rules. And we will pull apart how massive tech players are completely rethinking their physical hardware just to survive the sheer volume of information.
It is a really interesting tension. We build these incredibly sophisticated systems, assuming that making them bigger automatically makes them better.
Yeah, that's not that true, is it?
Not at all. The points of failure are often hidden in the most fundamental layers. It is about how data moves, how a machine interprets human intent, and, the literal physical limits of processing power.
So let us start right at that foundation. Moving data from point A to point B. What happens when the pipes look perfectly fine, the pressure gauges read normal, but the water just completely vanishes?
Right, the silent failure.
Yeah. I was reading the notes on ClickHouse distributed tables, and I just couldn't wrap my head around this silent data loss issue. How does a mission-critical database just lose data without throwing a massive red error code to warn you?
Well, the mechanism of the silent failure comes down to what the system is actually measuring.
Okay.
When you perform an insert into a ClickHouse distributed table, the system accepts the payload immediately. The pipeline sees that acceptance, registers it, and flags the operation as a success.
So it says, yep, got it.
Exactly. But the data does not immediately go into the final queryable replicated merge tree tables. Instead, it gets written as a .bin file in a temporary on-disk queue.
Okay, so it is basically sitting in a temporary waiting room. It hasn't actually made it into the main event yet.
That is a perfect way to look at it. And a background process is supposed to continuously flush that waiting room, moving the data into the actual database.
Right.
But problems arise when the ClickHouse keeper experiences downtime.
And what exactly is the ClickHouse keeper doing in this scenario? Is it, like, just the traffic cop for the waiting room?
In essence, yes. It coordinates the state across all the different servers. If that coordinator goes down or loses connection, the individual database replicas suddenly put themselves into a read-only mode.
Wait, why do they do that?
To protect themselves from writing conflicting data. It is a safety measure. But when they lock down into read-only mode, that background flush completely stalls.
Right. But the pipeline upstream has no idea the doors are locked.
None whatsoever. The inserts keep succeeding from the pipeline's perspective because it is only talking to the distributed table layer. And that layer is still accepting the data and creating those .bin files. So these files just silently pile up on the disk.
Wow.
Another way this happens, which is arguably more frustrating, is if a user sends an oversized insert block.
An oversized block, like trying to shove a couch through a standard door frame.
Very similar, yeah. If a block is so massive that it exceeds the memory limits of the background flush process, the entire queue gets blocked by this one massive chunk of data.
So it just gets stuck.
Exactly. The process tries to flush it, fails, and retries endlessly. Everything behind it is stuck permanently.
So it is basically like a delivery driver marking a package as delivered on their little scanner because they successfully took it down a storm drain.
That is a vivid image.
But it fits, right? The task is marked complete in the logistics system, but the actual payload is entirely gone. which, yeah, is exactly as terrifying as it sounds.
Well, a storm drain implies malicious intent, but technologically, the logic holds up. The system is measuring the execution of the handoff, not the actual safe arrival of the payload.
It just boggles the mind that in our era of highly advanced tech, a core database can swallow data like that.
It highlights a critical flaw in how we monitor infrastructure. We monitor the execution process rather than validating the outcome. And look, we see similar patterns happening in Google BigQuery too.
Really? BigQuery drops data too.
Yeah. Pipelines will report a successful run, everything looks green, but due to upstream API issues or partial load failures, massive chunks of data are just dropped silently.
So how do you actually catch that? I mean, if the pipeline is lying to you, who tells you the truth?
You have to step outside the pipeline's own self-reporting. Teams are solving this by using BigQuery's built-in information schema logs.
Okay.
And they combine that with a native function called AI detect anomalies.
Oh, interesting. So it is not a manual check.
No. Instead of relying on the pipeline to say it finished, you build a single central transformation script. That script constantly monitors the actual ingestion volume across hundreds of tables simultaneously.
Oh, I see the difference. So rather than writing a specific rigid rule for every single table that says, we must receive exactly 10,000 rows from the marketing platform,
Right.
the AI just learns the normal breathing pattern of the data volume.
Spot on. It builds a statistical baseline. It knows that on a Tuesday, this specific table usually ingests between 50,000 and 60,000 rows. If it suddenly only ingests 4,000 rows, but the pipeline still reports success, the AI spots the abnormal drop organically.
That is brilliant.
It is. It detects partial pipeline failures that traditional success checks completely miss, all without needing to integrate some massive external observability platform.
Right. So we fix the pipelines, the delivery driver stops throwing things in the storm drain, and the data actually arrives safely in the database.
That is step one, yeah.
But now we face a completely new bottleneck. Because increasingly, the person querying that data is not a human analyst. It is an autonomous AI agent. And apparently, they have absolutely no idea what they're looking at.
This is where human governance clashes violently with machine consumers.
Clashes violently. I love that. Unpack that for me.
Well, for years, data engineering teams have built extensive data contracts and governance policies. We define freshness rules, we set strict quality thresholds, and we write incredibly detailed semantic definitions of what a column actually represents.
Yeah, we write a whole paragraph explaining that revenue final V3 real excludes wholesale discounts and regional taxes.
Exactly. But the critical flaw is where we store those definitions. We bury them in configuration files or internal wikis or, PDF documents.
Right.
They're fundamentally human readable documents. To an autonomous AI agent trying to write a complex query in real time, those rules are completely invisible.
But hang on, I have to push back on this logic. We spend millions building these highly autonomous agents. We give them direct access to the database, but we are essentially handing them a locked safe and completely forgetting to give them the combination.
That is exactly what is happening.
How do we practically force teams to stop writing policies for humans and start writing them for machines?
It requires a fundamental shift in how we architect metadata. Critical governance elements must transition into machine-readable, queryable metadata.
So the AI can actually access.
Yes. If the AI cannot query the business rule via an application programming interface before it executes a task, the rule effectively does not exist. This gap in context is why we are seeing a staggering statistic. Over 80% of machine learning failures stem from poor problem framing, not bad models or poor data quality.
80%. That is wild.
It is huge.
So it is not that the AI isn't smart enough to do the math. It is that we have completely failed to give it the context to understand the business problem it is trying to solve.
Consider a case study of a real-world analytics agent. An engineering team built a highly complex system, but it only had a 45% reliability rate when answering business questions.
45% is terrible. You might as well flip a coin.
Exactly. It kept pulling the wrong numbers. But instead of rebuilding the agent's complex neural architecture, they simply fixed the underlying data models.
Really? Just the models?
Yeah. They gave the agent explicit, machine-readable rules for how to select specific date ranges and handle null values.
Just giving it clear mathematical boundaries instead of vague table names.
And that single change in context improved the agent's reliability from 45% to 86%.
That is massive. It proves that providing context is infinitely more valuable than just throwing raw compute power at the problem. I know Pinterest did something really clever with this exact issue.
They did, yeah.
They built an analytics agent that somehow managed to capture human tribal knowledge. How did they pull that off?
What Pinterest engineered is a masterclass in solving this semantic friction. They took over 2,500 queries that their senior human analysts had written in the past.
Okay.
They combined that historical query data with their governance metadata and AI-generated documentation. Then they processed all of that rich context into some kind of unified context intent embeddings.
Okay, stop right there. You're going to have to translate that for me. Unified context intent embeddings. What is an embedding in plain English?
Right, fair enough. An embedding is simply a way of translating words and concepts into numbers so an AI can plot them on a multidimensional map.
Okay, I am tracking with you.
What Pinterest did was map the mathematical relationship between what a user asks for in plain English and the actual complex logic required to get it. They created a centralized, semantically searchable knowledge base.
So if a new staff member asks the AI, how many active users do we have? The AI does not just blindly look for a column named user.
Exactly.
It looks at this mathematical map and sees that based on 2,000 past queries from senior staff, the concept of an active user always involves filtering out internal test accounts and bots using a very specific table join.
That captures the mechanism perfectly. The AI is operating with the exact same historical context as the human experts.
That is so smart.
And the results speak for themselves. This architectural approach cut their internal documentation effort by 70%.
Wow.
And it achieved a 40% user adoption rate. That level of adoption is incredibly rare for internal corporate data tools. It dramatically improved trust because the machine stopped hallucinating definitions.
Okay, so let us say we have achieved nirvana here. The data arrives perfectly. The AI agents fully understand the context and the governance rules.
A rare state of affairs, but let us imagine it.
Now we hit the wall of physics. Because the sheer volume of processing required to run these systems is forcing a massive rethink of hardware, right? All the way from the trillion-dollar enterprise down to the laptop sitting on my desk.
Yes. The physical infrastructure is no longer just a supporting detail. It is the primary bottleneck. If we look at the enterprise scale first, Anthropic provides a perfect case study.
What are they doing differently?
They have established a structurally superior compute stack by actively diversifying away from NVIDIA-only setups.
Which is properly wild, because everyone else in the industry seems to be fighting tooth and nail for those specific NVIDIA chips.
They are, and it is causing massive supply chain bottlenecks. Anthropic avoided that trap by securing long-term commitments with Broadcom, Amazon Web Services, and Google.
Playing the field.
Exactly. By leveraging AWS Trainium 2 and Google TPU v7 chips, they have built a diversified hardware foundation that delivers 30 to 60% lower per token costs than a comparable single-vendor setup.
That is a brilliant strategy. It is basically like refusing to buy all your groceries from one highly expensive boutique supermarket.
That is a good analogy.
By spreading your supply chain across different vendors, you give yourself unmatched negotiating leverage, cost efficiency, and, well, you aren't held hostage if one supplier has a shortage.
Right. The primary advantage is iteration speed. While competitors are delayed waiting for internal silicon programs or facing massive inference costs, Anthropic has over 2 gigawatts of dedicated compute capacity ready to deploy.
2 gigawatts. That is Doc Brown levels of power.
It really is. But this hardware revolution is not just happening in massive cloud data centers. It is happening locally, which brings us to the practical limits of DuckDB.
Oh, I love DuckDB. For anyone who hasn't used it, it is this incredible in-process database. It is the ultimate tool for anyone who wants to just get things done without spinning up a massive cloud instance.
It is very popular for a reason. Extensive benchmarking recently looked at how DuckDB performs on a standard $500 commodity laptop with just 16 gigabytes of RAM.
Just a normal everyday machine.
Yes. And they found a very specific sweet spot for warehouse-style columnar analytics on cheap hardware.
Okay, lay the numbers on me. What can a basic machine actually handle before it melts?
Well, for datasets between 1 million and 20 million rows, DuckDB delivers sub-second performance.
You are kidding.
No, it remains comfortably interactive for complex operations like grouping data and calculating percentiles.
Sub-second on 20 million rows. On a $500 machine. Mate, that is fair dinkum ridiculous.
It is highly efficient. However, at 50 million rows, you hit a clear physical boundary. At that volume, complex window functions start taking about a full minute to process.
Wait, sorry, I need to make sure I heard the scale of that correctly. We are running 50 million row analytics, executing complex window functions on the exact same cheap consumer laptops we use to binge watch Netflix.
We are. And here is the most impressive metric from that benchmark. Even when crunching those 50 million rows, the memory usage stays under 1.2 gigabytes.
That is unbelievable. I mean, my web browser uses more memory than that just keeping a few tabs open.
It is a common frustration, yes.
How is it physically possible to process that much information with so little memory footprint?
It is a testament to the physics of columnar storage and vectorized execution. Instead of reading data row by row, which loads a lot of unnecessary information into memory, it reads data column by column in dense compressed vectors.
Okay, that makes sense.
And DuckDB just released version 1.5, which pushes these boundaries even further. The standout feature in this update is the elevation of geometry to a native core type.
Geometry. So we are talking about spatial data, things like maps, coordinates, and complex polygons.
Yes. And to handle this natively, they introduced automatic column shredding for this spatial data.
Column shredding. That sounds incredibly aggressive.
Yeah.
Are we literally tearing the data apart?
Conceptually, yes. Imagine a complex three-dimensional map of a city. Instead of storing that entire map as one heavy monolithic object that takes massive amounts of memory to load, shredding breaks it down into individual lists of basic numeric coordinates.
Oh, I see.
It essentially unpacks complex spatial objects into primitive types under the hood for storage.
So it is like taking a massive, complicated Lego castle and breaking it down into individual bricks grouped by color and size.
Exactly.
It is much easier to store and retrieve all the blue 2x4s when they are shredded into distinct columns, rather than trying to stuff the fully built castle into a small box.
That is a perfect visualization. Because it is broken down into primitive numbers, it compresses beautifully. This single change reduces spatial storage requirements by up to 3 times.
3 times smaller. Wow.
And alongside other aggregate optimizations, version 1.5 yields a 17% throughput boost for standard analytical queries.
So we're doing significantly more work with a fraction of the hardware footprint.
Precisely.
But whether you are running a massive multi-agent AI system or processing millions of rows on a laptop, as operations scale up, you inevitably hit traffic jams, right? You need ruthless orchestration to prevent everything from just colliding and falling apart.
Chaos is the natural state of a high-throughput system. You have to actively engineer order into it. A perfect example of this software traffic jam is Uber's payment account processing.
What happened there?
As they scaled, they ran into an extreme hotkey traffic problem.
For those unfamiliar, a hotkey problem is when too many requests try to access the exact same piece of data at the exact same millisecond.
Yeah.
I always picture it like everyone in a massive city trying to buy an umbrella from the exact same shop the second it starts raining. The shop simply cannot process everyone at the door.
In Uber's case, high-activity payment accounts were hitting sequential processing limits. Every time a transaction occurs, the database has to lock that specific row to ensure financial accuracy, process the math, and unlock it.
Right.
That locking and unlocking mechanism takes physical time. Because of this lock contention, they were capped at 3 to 4 operations per second per account.
That's so slow.
That bottleneck was causing bulk financial jobs to take multiple hours to process.
3 to 4 operations a second is painfully slow for a global operation like Uber. How do they actually untangle the traffic jam?
They implemented a 3-service architecture that batches financial updates into roughly 250 millisecond windows.
Okay, quarter of a second.
They use a system called Redis for coordination and queuing all the incoming requests. Then, instead of writing them one by one, they execute a single atomic write per batch to the main database while offloading the immutable audit logs asynchronously.
Oh, I get the physics of that now. So instead of opening the shop door, letting one person buy an umbrella, locking the door, processing the payment, and repeating that 10,000 times,
Right.
they just hold the door open for a quarter of a second.
Yeah.
They let everyone shove their money in a bucket, process it as one single atomic chunk, and then close the door.
It reduces the database friction immensely by minimizing the lock contention. We see a similar need for strict orchestration in Apache Pinot's real-time data ingestion.
What is happening with Pinot?
When you have multiple server replicas consuming data from the same continuous streaming partition, you risk massive data inconsistency.
Because 2 servers reading a live stream might process the data slightly differently, or, one server might experience network lag and fall behind the others.
Exactly. To solve this drift, Pinot guarantees a single, consistent winning segment using a lightweight, controller-orchestrated blocking commit protocol.
A blocking commit protocol. Break that down for me.
The controller acts as the absolute authority. It looks at all the replicas and elects a committer based on who has the maximum offset.
The maximum offset. Meaning what?
It simply means the server that has read the furthest into the stream and is the most up-to-date. Once that server is elected, the non-committers simply discard their local, potentially flawed versions and download the official winning segment from the leader.
It is absolute, ruthless consensus. There is no debate, just one source of truth.
Exactly.
But orchestration is not just for database transactions anymore. We are now having to orchestrate fleets of AI agents. I was reading that scaling beyond a handful of agents gets incredibly messy very quickly.
It degrades rapidly, yes.
Yeah.
Research shows that once you scale a system beyond 15 distinct AI tools or across 3 conflicting knowledge domains, standard AI routing breaks down.
It just can't handle it.
The system gets confused about which tool to use. You have to switch to an architecture known as a conductor specialist pattern.
Which makes perfect sense when you think about it. It is like moving from a solo acoustic musician to a full symphony orchestra.
Very much so.
You cannot just have 60 musicians randomly guessing when they should play their instruments. You suddenly need a conductor who knows exactly when the brass section should come in, or in this case, exactly which specialized AI agent should handle the user's specific request.
That is the exact architecture. A system called Volt Agent acts as the orchestrator, or the conductor. It relies on a highly unified storage layer, often using something like SerialDB.
And what does SerialDB do differently?
It fundamentally combines vector, graph, and relational data into one engine.
Wait, why do you need all 3 distinct types of data storage just to route an AI agent?
Because a single approach is insufficient for complex reasoning, hybrid retrieval significantly outperforms any single method.
Okay.
An optimal mix for the orchestrator might be relying 60% on vector search to find conceptual matches, 20% on graph databases to understand the strict relationships between entities, and 20% on exact relational keyword matches.
So it is using every trick in the book.
Yes. This dynamic, multi-layered task routing ensures the orchestrator sends the task to the right specialist agent. It keeps compute costs under control and completely prevents the system from hallucinating due to tool overload.
It is brilliant. We started this conversation talking about simple pipelines that silently swallow data into a storm drain. And now we are talking about literal symphonies of AI agents perfectly passing complex tasks between each other, based on mathematical graph relationships and vector searches.
It is a massive leap.
It really shows how far down the rabbit hole this architecture goes to maintain the illusion of seamless scale.
It is a continuous, relentless evolution. As we solve the physical bottlenecks of hardware and lock contention, we uncover new logical complexities in semantics and governance.
Right.
Which then require entirely new physical optimizations to process.
It never stops. So I will leave you with this thought. Next time you write a data governance policy or define a metric for your team in a PDF, ask yourself, could an autonomous machine actually understand this context, or are you just writing it to make the compliance team feel better? Keep questioning your systems, keep tweaking your setups, and interrogate the things that look perfectly fine on the surface.
And until we speak again, you might want to double-check if your internal business intelligence dashboards are genuinely secure, because vulnerabilities like the zero-click leaky looker exploit have proven that attackers can manipulate and steal your cloud data without you ever clicking a single malicious link.
Spoken Tech, for your ears.